Okay, morning. Let's continue on complex number. Let's finish it today. Okay. So we talked about Euler's formula in the previous lecture. Euler's formula, essentially you can write a complex number into the Euler formats. For example, if you have a complex number which is cosine theta plus j sine theta, it can be written as e to the power of j theta. Okay. And if you change the theta to omega, then you get cosine omega t plus j sine omega t. Okay. And for a typical complex number, and here's your complex number a plus jb, which has two components. So when you have a complex number, it always has two information. One is its modulars. The other is called its argument, theta. So r equal to absolute value of z, and theta equal to the inverse tan b over a. Then your z can also be written into this using Euler's format, which is r times cosine theta plus I sine theta. That's your z, which can be written as, okay, in the Euler's format, r times e to the power j theta. And one more format, this is also equivalent, is we write an r and an angle theta. Right, so that's the same as this. Okay, so when you see an r angle theta, meaning r times e to the power of j theta. Okay, this is what we learned in the previous lecture. Now what we're going to do is, right, so essentially we consider, let's say, given a sinusoidal curve, sinusoidal function or signal. Let's call it v of t equal to a times cosine omega t plus phi. Or maybe even more, let's say we have another one. Let's call this is v1. Let's consider we have multiple ones. Okay, let's consider two. We have two sinusoidal signals. And now what you want to do, see, what would be the addition of the two sinusoidal signals? Okay. Even though they're cosine, we still call it sinusoidal signal. Okay. All right. So, well, how would you add up two sinusoidal signals? Okay. So first of all, when you have a sine signal, it has a magnitude, it has a frequency, and it has a so-called, what's this term represent? Phase. Yeah. And they can be different phase, right? They can be different amplitude, but in this case here, we consider both has the same frequency. Okay. So how do we add these two signals up? That's the point here. To do this, we can actually, I'll show you, to use this so-called the phasor representation of sinusoidal, which involve the Euler's formula to help us by adding these two up. Right. But before we add up, one thing you have to be sure is when you have two sinusoidal signal with the same frequency but different amplitude and the phase, when you add them up, you will get another sinusoidal signal with a different amplitude and a new phase, but still the same frequency. Okay, so that you have to be clear. Okay. So how do we do this with the phasor concept? As we learned in the previous lecture, phasor basically, okay, so phasor right here, it's referred to the A, E, J, phi. Okay, so now let's go back to a general sinusoidal. Okay, phasor is this. Okay, for for a general sinusoidal signal. Now the reason is because when you are given this sinusoidal signal, which is A times cosine omega t plus phi, and that's basically the real part of a complex number. And that's this real part of this complex number will give you this sinusoidal signal. And I can manipulate this term a little bit because this is the e to the power j omega t plus j phi. So e to the power of a plus b equal to e to the power of a times e to the power of b. So I can separate that complex number into this format. And then you have this term explicitly showing up. That's what we call, this is a phasor, for v of t. So e to the power of j phi is the so-called phasor for v of t. This is actually the basis of what we're going to use to finish or to obtain the results of this addition of the two sinusoidal signals. So let's see how we're going to do this. I'm going to use an example probably to show you how we're going to do this. Let's consider let's consider here. How do we get the results of these two sinusoidal? So this one minus this. This is exactly what I showed you here, right? V1 plus Vt. So the two minus each other. They have different amplitude, different phase, but the same frequency. To do that, we will use this phasor concept, this one here. So first of all, for the first one, well, anyway, let me just start from beginning. So what's the first one? This is 3 times cosine. This is the real part of what? 3 times e to the power, right? Let's relate to here. So when you have a cosine omega t plus phi, this is a real part of the a times e to the power j phi, and then times e to the power of j omega, right? So this is the j. We'll start from beginning. Omega t here is 20t, and phi here is 10 degree. This is the first part. That's 3 times e to the power. This is the real part of this. Give you back this original sinusoidal. And the second one here, I can put it in the same bracket here. The real part of what? Phi times e to the power j 20t minus 30 degree. So now let's manipulate this inside the bracket here now. So far so good? Any question at this step? From here to here is okay? So for this first term, we can separate that, take the phasor out, right? So this is 3 times e to the power j 10 degree 20t, and 5 30 degree 20t. And now we have a common factor, right? This is a common factor. E to the power j20t is a common factor, and I can extract this common factor out. Inside the brackets are the rest of the term. Okay. So up to this stage, okay, what we did is actually we separated the constant, not a constant real number, constant complex number. We separate the constant complex number from a variable complex number. So you see here, this is a t, right? So we don't know what the t is, but this is cosine 20t plus sine 20t. This is a time changing complex number. But this one here, inside the bracket, this is constant 10 degree, and that's negative constant 30 degree. So this whole thing should give us a constant complex number. Okay? So let's try out. And then what is the complex number associated with this one, right? So together, when you do this together will give you basically another complex number. Okay? That's the point. So let's calculate this here. Okay, that's the idea. So I'm going to use a separate line here to deal with this bracket here. Okay? Yeah. So first one is 3 EJ 10 degree minus 5 EJ negative 30 degree. Okay, so this is the term. So let's look at it. What does this term give us? Just remember, this is essentially a complex number minus another complex number, which should give you a back complex number. This is 3 times what? Cosine 10 degree minus plus j sine 10 degree. That's the first term. And the second term is 5 times cosine negative 30 plus j 5 times negative 30. Using Euler's formula to write back the complex number. So now you can use your calculator. Okay, so this time you do need a calculator. But when you use a calculator, make sure the calculator is set to degrees, right? Not the readings. So you use a calculator, you calculate each one of the term, and combining all the term, you should get a this is not going to be a very integer number, so it's be a negative 1.3757 plus j 3.0209. Okay. So I'm using 4 decimals here. Okay. So that gives us back a complex number, which is this. And then for this complex number, you can write it back into the phasor format. So you can use its readings, you can call it A or whatever, you can call it R, that's okay. You can write it back into a magnitude and the angle, right, using the Euler's format. So how do I do this? You can roughly plot this. This is x is negative, y, so this is somewhere here, right? Somewhere here. That's your complex number. Okay. So I need the r, and I also need the theta or phi, whatever you want to call it, right? And r at here is basically the magnitude of this complex number, and that gives us approximately 3.32. And the theta at here, okay, theta at here is this angle here. The formula is inverse tan b over a, which is what? B at here is, this is b, What happened here? Okay. B is 3.0209, and then over the negative 1.3757. Now, when you use a calculator to calculate this one here, okay, you got to also kind of be careful here. When you use a negative angle, your calculator might give you a negative angle, but you have the graphite here, right? So your actual theta should be an angle somewhere a little bit less than 180 degree, but more than 90 degree, right? So you should be you should get a number, okay, from your calculator that makes sense, because calculator doesn't know, where your actual theta is, right? The calculator will give you just a solution. Okay? So that should be your theta, 114.5 degree. So this is your R and this is your theta. Basically, the term inside this bracket, okay? So let me rewrite it again. So V of t, which is the real part. Okay. So that whole term, right, in the bracket, here is 20t here, can be written now as R times through 3.32 e to the power 114.5 degree. Okay. That whole term in the bracket can be written as this. And write down the EG20t here. Okay, so now everything is easier now. So then you get this e to the power j 20t plus 114.5. So now altogether, what's the v of t now? Right, v of t is the real part of this complex number. So v of t should be 3.32 times cosine 20t plus 114.5 degree. Now you get the results. Basically, now you successfully obtained the addition of these two sinusoidal signal. Okay. I also want to caution you here. Typically, we don't use a degree. You use a reading here. This number should be always a reading. But just be careful, because sometimes when you put 20 times t, it actually give you back a reading. So a little mismatch is not. But anyway, so I use a degree here. Okay. Is that clear? Okay. So when you have a Euler, when you write the complex number into the Euler's format, you actually can use it to simplify addition of two sinusoidal signal with a different amplitude phase but the same frequency. If the frequency is different, you actually can use this approach. Okay, you can use this approach. If the frequency is different, you actually cannot obtain. When you add two sinusoidal with two different frequencies, you can't end up with one signal, right? So it will be one signal with multiple frequencies. Okay, that is Euler. So now let's take a look at another application of Euler here, okay? And that is called the nth root of a complex number. Before we do that, but there is another concept called the nth power of a complex number. Okay. This is also a very useful formula. So for example, if we have a complex number a plus jb, and you're interested in saying, so what is the power of n, right, of the z to the power of n? So if I want to do this, okay, so then what would you do? Your typical approach is Okay, so a plus jb times a plus jb, and then times a plus jb, and then times a plus. So you multiply by n times, right? Yeah, that's what you do, right? And you can imagine if you multiply 10 times, then you're probably going to spend the whole morning just to do the calculation, okay? But I do have a shortcut. I can write this complex number into this Euler's format, okay, r times e to the power of j theta. And now, if I want to calculate z to the power of n, and things are becoming very easier. So r e to the power to the n is r to the power of n, and then e to the power of what? N theta. Right? So this is much faster to calculate, right? Yeah. And once you get this, you can write it back into a standard complex number format, right, from here, and that's much easier. Okay. So that's called the nth power of a complex number. And there's also, right, instead of just the power, you also have the so-called the nth root of a complex number. Nth root of a complex number. Now, what does the nth root of a complex number means, right? So here is the idea. Okay. So for example, right, let's use a real number, x equal to 4. And by the way, real number is a complex number when the imaginary part equal to 0, right? So if you have a x equal to 4, and we will see, so what is the square root? Okay, what is the square root? Basically means what's the second root? Okay, the nth root, right? First root, second root of x equal to 4. Okay. Is that good? Yeah. So it's like this. So basically, you're looking for a value. You're looking for a y, and whose square will equal to 4, right? So basically, if this is y here, that's the second root or square root. You're looking for the answers to y such that its square is 4. So y equal to what? To 2 and negative, right? So there are 2. Basically, here there are 2 square roots, right? 2 second roots for x equal to 4. And of course, if I phrase it differently, if I consider this as a complex number, okay, 4 plus 0j, then the second root of this complex number is positive and negative 2. Okay. Okay, but I want a more general solution here. Okay, so let's consider a general complex number. So consider this complex number, which is of course same as this. Okay. So here's a complex number. So what do we want, right? We want to find another complex number. Let's call it w. And w can be written as, just like the z, can be written as a general complex number with the magnitude and also the angle r and theta. So we want to find a w at here, such that, remember this is the nth root, so such that the w to the power of n equal to the z. Okay. So then w can be called the nth root for the complex number z. Okay. So this is why w is the nth root of z. This is basically the new objective here. Okay. So let's see how we can find this question here. So we need to rephrase it as a solvable format. Okay. So w to the power of n equal to z. Here's your w, right? So w basically can be w to the power of n. This is your w. I don't know what w is yet, but I can always write the w into the Euler's format. Okay. So rw e to the power of j theta w. We need to find rw and the theta w here, basically. And this power will equal to z, and z is this term, so rej theta. Good? Yeah. Now, even better yet, if you recall, if you look at this z here, this is a cosine theta, this is a sine theta, right? Yeah. Now, sine theta, cosine theta, they are all what? Periodic function. So if I plus 2 pi, it doesn't change. It's still the same complex number. That make sense? Or if I multiply a multiple of this 2 pi period, then it's still the same complex number, right? So basically the theta go back, go one term, another term, you go back to itself, okay? So I'm going to do this. I'm going to add a 2k pi at here. Okay? The idea is I want to find all the possible n roots for the z, not just one. Okay? So we add a 2k pi. K can be 0, can be 1, can be 2. As you can see, for different question, you will take different numbers. Okay. And actually, k is limited by the n at here. Okay. Okay. So now I have rephrased the original question into this expression now. So this times this times this to the power of n equal to this. So let's simplify this. I got rw to the power of n and ejn theta w equal to r e to the power of j times theta plus 2k pi. Always remember which is known, which is unknown, okay? The right side is the known value, so r and theta are known. You should be able to get it from based on the given complex number. And then this is naturally means your rw to the power of n should be the same as r, or your rw is the nth root, right, of the r value. And n times theta w should be the same as theta plus 2k pi, or theta w should be theta plus 2k pi over n, right, over n. So now as you can see here, the k can be 0, can be 1, can be up to maximum n minus 1. Because when k equal to n, then what happens is 2n pi over n equal to 2 pi. So then it becomes theta plus 2 pi. So that's basically a period, right? Then you don't need to keep increasing k anymore. Because once k is more than n minus 1, then you have a multiple of 2 pi here now. Okay. So then you don't have to, because the period always come back to itself. So that's the maximum k value, n minus 1. Okay. So basically, here we got a solution now, right, for rw and theta w. Okay. So let me give you an example here, and then we'll see what happens here. Okay. So basically now your w equal to, right, r to the power of 1 over n, and then cosine theta plus 2k pi over n, and then plus j sine theta plus 2k pi over n. Okay, that's your solution for the W. So let's take an example. I want to find the fourth root for z equal to -1. Fourth root. So before we solve it, okay, let me go back to the general solution at here. So you should actually, in your mind, before you actually go into the solve it here, if I'm looking for the fourth root, so the n at here equal to 4. So if I'm plugging over here, so k equal to 0, 1, 2, 3. So 4 minus 1 is 3. So you have 0, 1, 2, 3. So you should have 4 different solutions for this question. Okay, that's the concept here. Okay, first step, z equal to -1, but don't be surprised that that's not a complex number, right? It is a complex number, right? So it's a complex number, and this complex number, where is it? It's over here. So for this complex number, what's the r value? 1. What's the theta value? Pi. Right? Very good. So you basically you're making use of the formula here, right? You're making use of the formula. Then basically your z equal to j pi, or cosine pi plus j and sine pi. So now I'm going to make use of formula right here. Okay? R to the power 1 over n is r to the power 1 over 4, and r is 1, so you end up with 1 again. So your w equal to cosine, okay, over here this is a formula, so theta plus 2k pi over n, which is 4, and plus j sine theta plus 2k pi over 4. Now we're going to change the k from 0 to 1 to 2 and then to 3. Okay. So this is what we're going to do. There's no point to be more than 3, because once you're more than 3, it becomes 2 pi, right? It's become a periodical. So this way, right, you guarantee that w to the power 4 equal to 1. So let's take a look at what's each one of the w at here. For the first one, when k equal to 0, this term is 0, so just a theta over 4. Sorry, what's the theta value? Theta is a pi, right? Can I replace the theta with pi? Okay, let's replace the theta with pi here. Okay. So when k equal to 0, you get cosine pi over 4 plus j sine pi over 4. So this one you don't need to always write. You can write it, just keep it at this, that's fine. Okay. And then for W2, it's going to be cosine 3 pi over 4 plus j sine 3 pi over 4. For k equal to 2, so that's cosine 5 pi over 4 and sine 5 pi over 4. And the last one will be 7 pi over 4. So 4 different solutions. Each one of these to the power of 4 will be equal to -1, which is the original complex number. Now graphical wise, okay, you can actually graph them out for this one here. So W1 is at pi over 4, W2 is at here, and W3 is at here, and W4 is at here. Okay. So basically if you're looking for nth root, 4 or 5 or 6, you have 6 answers and 6 complex numbers and answers. And these numbers will evenly divide your complex plane into 6 sections. Okay. Or in this case, 4 sections. Right. Okay. Is that good? Yeah. That's the idea of the nth root of a complex number. Combining, right, the idea of nth power, don't mix that with that concept. Okay. As you can see, the Euler's formula is a very useful format. Okay. We use it a lot, actually, try to simplify things. Okay. In my lecture notes, I do have another one, but I don't think I'm going to go into the details. This is for your own interest, just to show you the beauty of mathematics. So you can take a look at it without going into the details here. There are many things that actually relates to complex number. One of the things is called, in mathematics, called fractal. Have you heard of fractal? Anybody heard of fractal? Yes. What is fractal? Exactly. Yeah. So if you observe a tree branches, right? So it keeps branching out. You have a smaller, a bigger, but if you zoom into the smaller one, and you will see the same pattern as the big one, right? And that's basically called fractal. It's like a universe. You take a grain of sand. It's a grain of sand, but if you zoom into it, there's probably another universe in it, right? So complex number here, there's so-called Julia set and the Mandelbrot set. The Julia set equation is this. So you have a complex number. You form a so-called a recursive equation. You see here? So the next one equal to the previous one square plus an initial constant. Could be a complex, could be a complex, could be a constant real number. Right? So this is a recursive one. So this can be calculated continuously as much as possible. Okay? So if you plug in initial c, and you'll get the corresponding z values as many as possible, right? Yeah. And then you can plot the magnitude of the z, okay, and using MATLAB, and then to basically using certain function to plot them out. Okay. And you for different c value, initial c value, you'll get a different graph. For this c value, I think the graph of the c is c equal to 0.745. If you change the c, you get a different values here. This is called a fractal artistic picture. If you change the c, you get completely different ones, really beautiful different pictures, right? And that's actually really interesting. If you zoom into each one of the area within this graph, you'll see a similar basically patterns as you see in overall. Right? So that's fractal, right? And many things. This is the reason why math is beautiful. You somehow just can relate many things together, right? And use it to describe some of the real problems, right? We often see, why do we learn mathematics, right? We don't really use this in our real life, but in many situations, you definitely need that to explain it. Okay. So this just for your own interest, okay, and you can certainly explore a little more on yourself. Okay, now we've finished complex number. Let's continue with ordinary differential equation. So we finished first order now. So now let's continue into the second order ODE. Okay. Second order ODE, I'll give you a couple of examples at here where second order ODE come from. This is a mass spring and damper system. We have learned a little bit about how to set up a mathematical model for a simple mass spring damper system. And for this system here, you can set it up, which is mx double dot plus bx dot times kx, and then equal to f of t. Okay. So f of t is the external force input. X is the motion due to this, all the external forces coming from f of t spring and the damper. Okay. Then you end up with this second order differential equation. Right? You've got the second order derivative here. Okay. And very similarly, you can also use an electrical circuit, RLC circuit. You get also similar second order ODE. Now, of course, the question here is, okay, how do I solve this, right, to give me specifically a solution for x of t? Because you're interested in, okay, if I apply this force, and how does this mass move? It may move at a sinusoidally or move at just arbitrarily different trajectory, right? Depends on the f of t. Okay. So the question here is, we want to solve for this x of t. Now, in general, second order equation looks like this. So y double prime plus p of x y prime plus q of x y and equal to f of x. Okay. So this is the sort of the standard format we will use. Okay. And you can always convert any ordinary differential equation, okay, into this standard format. Okay. Now remember, we're talking about ordinary differential equation, and in particular we're looking at the linear one here. Okay. So linear basically means the coefficient for every one of the derivative term cannot be a function of y. Okay, it can be a function x, not a problem, but you cannot have a y square here. That's not going to be linear, right? Okay. So for this general one, there are two cases. Case number one is when your f of x equal to 0. So no input, right? No input to the system. And we call this case called homogeneous. So this is a homogeneous case. And you will only have the p of x and q of x at here. And the system will mostly be driven by initial conditions. If you don't have any initial condition, the system will stay still, right, in this case. And we'll also look at another case when the inputs, the right side is not 0. And we'll call this as non-homogeneous. Okay, non-homogeneous case. So for the next couple lectures, we'll look at the homogeneous first, and then we'll look at non-homogeneous next. Okay. Okay. Before we can solve for this, I need to introduce a couple of concepts first. Okay, just to set up the stage. First couple concepts called general solution versus particular solution. General solution and particular solution. Now this is the part that's for second order ODE, but different from your first order ODE. Okay. So let's start with this homogeneous one here. Okay. So here's the homogeneous one with the input set to 0. Okay. So I'll give you one example here. Let's see if I have a system like this. So I changed the x and the t's, okay, but you should understand that's just a dependent variable, independent variable. Let's say you have a second order ODE like this. Okay. Now without knowing how to solve it, I'll give you a solution. So I can get a solution. You'll see that y1 of t equal to cosine t is a solution. Okay. And y2 of t equal to sine t is also a solution. So you can try it. I mean, you can substitute cosine t into this function here, into the equation here. So cosine t derivative is negative sine t. And negative sine t derivative is negative cosine t. And then plus cosine t is 0, right? So that satisfies the equation. Sine t plug in here, cosine t, and then another derivative negative sine t. Negative sine t plus positive sine t is 0. So that's still a solution, right? Yeah, both of them are solution. And if you multiply cosine t with 2, you'll see it's still a solution. And same thing, if you multiply sine t with 3, okay, and that's also solution, right? So all of these ones here, as you can see, right? All of these, what we call them is a particular solution. So all of this here, we call them particular solution. Okay. So you can, congratulations, you get a particular solution, but that's not the end of the day. You have to find the so-called general solution for second order ODE, right? So what we need is a general solution. So we need and this idea applies to all of the future basically ODEs even it's not homogeneous, okay? Now what would be a general solution then? A general solution here, as you can see, is you can do this. You use a general constant C1 times cosine t, and then plus the general constant C2 times sine t. Now this will give you, this is a general solution for the given equation. So without knowing how to solve, we'll show you later here, okay? But this is a general solution. Why is it general? Because now you see I don't have a specific constant numbers here, right? I have two general constants. And they also involve both cosine t, sine t. So in other words, what we just write here will actually contain all of the particular solution. Right? If you think about it, if I let C2 equal to 0, C1 equal to 1, you get Y1, right? If I let C1 equal to 0 or C2 equal to 3, then you get a Y4. So this general one has all of the possible particular solutions. That's why it's called general. Right? Yeah. Okay. I think I'm going to stop here. So we need to have two theorems before we can officially start solving for second order ODE. Okay. Yeah. Any questions?